All right, when we talk about equilibriums, we're talking about an equilibrium reaction. And equilibrium reactions are reactions that go both in the forward and the reverse direction, right? Which means that if we have a reaction like this one, 2A goes to 3D, that at any one time, the A's are coming together to form D's, and the D's are reforming A, right? So the reaction itself is continuously moving from A to D. Right? Once we reach equilibrium, what that means is the rate of the forward reaction, right? So if we look at this 2A as a solid, if we talk about it in terms of the rate constant, lowercase k1, right? And the reverse direction being lowercase k2, right? At equilibrium, the rate of the forward is equal to the rate of the reverse, right? Which means that in this reaction, it appears that the concentrations end up going to a specific value, right? And that depends on the reaction and the temperature. But we're going to get a relationship between the amount of products and the amount of reactants that's going to be constant based on whatever this rate is. But it appears it's referred to as a dynamic equilibrium because the reactions themselves do not stop. They just appear to become stagnant because the concentrations remain the same. Okay. So when we look at this, we can also define this equilibrium position, the relationship between products as reactants, as being equal to now capital K, as being the concentration of the products raised to some coefficient divided by the concentration of the reactants raised to some coefficient. Right? So when we look at this, we can say that in the relationship between those two in terms of concentration is going to be some value which we are calling capital K, right? And we were going to see through the next 8 lectures that we're going to have a whole bunch of different names or specific values. This called, if we want to talk about a generic or general equation, we would refer to that as KEQ, right? The equilibrium constant for some equilibrium expression, right? We're also going to have things where we talk about it in terms of concentration. We would call that capital KC. If we talk about it in terms of pressures, that would be capital KP. If we talk about an acid, we're going to call that Ka. If we talk about a base, it will be Kb. If we talk about a solubility, it's going to be Ksp. Right? All of these are going to be related, but they have this general form. Right? So we want to be able to calculate a value for this equilibrium constant for this reaction. Right? And this reaction, the equilibrium expression, in general, is going to be products over reactants. So this is going to be equal to the concentration. Oh, can't use an eraser to write. Concentration of D raised to the coefficient in front of it, 3, divided by the concentration of A raised to its coefficient of 2, right? That would be the so-called Kp, or Kc, excuse me, right? Because this is in terms of concentrations, we would call this Kc. But if we look at concentrations, what it means to be in a concentration, it means that we want to know how much of that species is dissolved in a solvent, right? If we look at A, A is a solid, right? And because it's a solid, it means it's not in the solution. Therefore, its concentration we could not define a concentration, so we don't include this. Right? So in these equilibrium expressions K, we ignore pure solids, and liquids, right? Because they are not part of the solution or they are not in the gas, right? So if we refer to this as the Kc in terms of concentration, that it would be equal to the concentration of D cubed. Because A is not in there, we would essentially set that value to 1. If we looked at this in terms of Kp, which means that we're talking about the equilibrium amount in terms of pressures, then the only thing we would be concerned about with those that are gases. So now we would be talking about the partial pressure of D, but again, it has a 3 in front, so it would be cubed. Again, A is a solid, has no partial pressure, so it would not be included in our equilibrium expression. Okay. So, does that make sense? Questions on this general equilibrium ideas? Okay. So, waiting for questions? No questions. All right. So now if we look at this, or what we're trying to do in this problem, we're trying to determine the value of this, right? We want to know this number. We don't have any information about the equilibrium conditions, but what we do have is a series of 2 other reactions, and we have their K values. Right? So if we look at these 2 reactions, and I'm going to copy them back down here, right, where we have A as a solid is in equilibrium with 1/2 B as a gas plus C as a gas, and 3D goes to B. Oh, this is a gas, excuse me. 3B, or B is a gas plus 2C as a gas, right? As before, if we can find a way to combine these 2 reactions in order to get this reaction here, then that's going to allow us to say something about the combination of those 2 should say something about the third one, right? So when we do that, what do we have to do to these 2 reactions to get this reaction up here? If we look at the first one, right, we look at this reaction at these 2 places, right? In this lower equation, we only have a single A as a solid. In the top one, we have 2, right? So at least we're going to have to multiply this whole reaction by 2. If we look at the bottom reaction now, compared to the reaction that we want, now we see that the only difference between this D and this D is that one is a reactant, one is a product, right? So that means we have to reverse it, and if we go to what we've done in the past, when we reverse it, we multiply it by a negative number, right? So that's going to mean now we're going to have 2A as a solid is in equilibrium with 2 times 1/2 is 1, B as a gas plus 2C as a gas. And the second equation we're reversing, so we're going to end up with B as a gas is in equilibrium, or excuse me, can't read, plus 2C as a gas is in equilibrium with 3D as a gas, right? So now if we combine these, this is going to cancel with that, and this is going to cancel with that, right? So we're going to end up with 2A as a gas is in equilibrium with 3D as a gas. Okay. Everybody follow that? Okay. Well, then if we know you can combine these two reactions together to get the final reaction, then we should be able to combine their equilibrium constants in some way in order to determine the equilibrium constant of this third reaction, the reaction that we want. Right? So let's look then at these equilibrium reactions here and see what happens when we do some of these things that we did. So if we look at the K for this first equation, right? This first equation here, before we've done anything, if we write the equilibrium expression of that in terms of the pressure, that is going to be equal to the pressure of B raised to the 1/2 times the pressure of C raised to the 1, right? A is still a solid, so we don't include it. If we come down here where we've multiplied it by 2, now our K is going to be equal to the pressure of B raised to the first times the pressure, can't talk and write at the same time, the pressure of C now squared. So what did we have to do to this equation to get that? Well, if we're taking this one and it starts as a single value here and doubles there, the only way we can do that is by squaring this, right? So to go from this KP to this, we're going to have to take that number and square it, right? So when we multiply by 2, we are going to raise that number by 2. So if this value was 0.0334, then this value is going to be equal to 0.0334 squared, right? Which is equal to 1.116 times 10 to the negative 3. Okay. Everybody okay with that? So if we multiply a reaction by a number, we end up raising that equilibrium constant to that number, and that's how it changes. Right? Okay. Now let's look at this second one. If we look at the K expression of this, let's change that back to a different color. If we look at the K expression of this one, right, then for that reaction, Kp is going to be equal to, I can't remember off the top of my head, B, the pressure of B times the pressure of C squared divided by the pressure of D cubed. Right? The pressure of B times the pressure of C squared divided by the pressure of D cubed, right? That's this top one here, right? Products over reactants. If we look at it down here now, our pressure, can't say that, our equilibrium expression in terms of pressure is going to be the pressure of D cubed divided by the pressure of B times the pressure of C squared. To move from here to here, right, that's taking 1 divided by K, right? We're inverting this. So when we reverse this reaction, we go, what was products is now becomes reactants, the K expression inverts, right? So if this number up here is equal to 2.35, equal down here is going to be 1 over 2.35, which is equal to 0.4255. Okay. Pretty okay with that. So when we multiply these equilibrium reactions by a constant, we end up raising their K, their equilibrium constant, by that number. When we reverse it, we invert. So now let's look at what we have to do when we combine this one and this one to get this. Right? If we add them together, that's not going to work, right? Because we'll be adding essentially 2 fractions, which would be not this. In order for this reaction to occur, we have to cancel out this part, right? Which means we have to, this Kp of the final is going to be equal to K of the first one times K of the second, or the pressure of B times the pressure of C squared times the pressure of D cubed divided by the pressure of B, pressure of C squared. Now these two cancel out, and we're left with the pressure, partial pressure of D cubed. Right? So if we're multiplying these two together, our Kp of our equation we want is going to be equal to 1.116 times 10 to the negative 3 times 0.4255, which would be equal to 3.25 times 10 to the negative 8. So when we combine reactions, if we add those reactions together, we end up multiplying their equilibrium constants. If we subtract reactions, we would end up dividing those equilibrium constants. Right? A couple other things to point out as we're talking about this, all of these equilibrium expressions, regardless of whether it's Kc, Kp, Keq, Ka, are going to be unitless. We do not assign units to any of these values. So this is the one time when we talk about these equilibrium expressions, you can totally ignore units. Right? All of these are just going to be a relationship, right? A fraction of sort of mass, if you will. So we're not going to talk about units. Okay. Also, if we look at this K expression, maybe give it to me. Right, if we look at these K expressions, we can define about which side, or just talk about which side of the equilibrium is favored. Is it going to be reactant favored or product favored? If these reaction if capital K is greater than 1, right? And if we think about these equilibriums being the products over reactants, if K is greater than 1, that means we have more products than reactants. This is referred to as product favored, right? Which means we're going to have more products than reactants. If K is less than 1, now in order to get less than 1 to be some number less than 1, we have to have more reactants than products. So this one is referred to as reactant favored. And at equilibrium, we're going to have a higher concentration of reactants than products. This first one, we're going to have, in this case, we would have a larger concentration of products than reactants. Any questions about that? All right, so for today's activity, we are going to be either defining these